we start with tutorial 5. We have 4 questions. So first question is okay. We have power systems using the pumps, the hydroelectric that pump back of the water. So I think it's common if we have excess energy and want to store the energy. So it's not converting from mechanical energy into electrical, but we change from the electrical into mechanical. Sometimes it's available for water reservoir systems that we need to store the energy instead of using battery. We use the water reservoir. So it's a common with if we not really discuss about it. So we have a storage reservoir starting from point 1 to point 2. And from point 1 and point 2 has elevation difference of 100 meters. And then the flow rate required to make a flow rate from point 1 to point 2 is 150 meter cubic per second. So this is the flow rate. And then the total head loss due to the frictions, because we have pumping here. So the losses is 20 meter equal of the losses. And the efficiency of the motor pump 85%. And we need to estimate the electrical power input to the motor required. So first we need to define what is the power from pump, and the next is what is power for the motor. Because pump is the actual power and motor is input power. We have efficiency 85%. So pump must be get lower than the motor, or motor must be higher than pump. So we have assumptions that the system is steady, incompressible, and adiabatic, and constant water level. The meaning constant water level is mean even though we take flow 150 meter cubic per second, the things of their elevation is not really varying. So we can assume that the level is correctly constant. So it normally happens when we have very big reservoir and the things of 150 meter cubics, not really much changing the elevation. For the example, we have very wide, like 100 hectare square and so on. And the next is we input the steady flow energy equation, so our Bernoulli equations. It depends on how you call about it. So we have the balance. This balance from point 1 to point 0. The things of if we have anything of pressure, velocity, and elevation will be equal with the total of frictions or losses minus pumping and plus 2. So it means turbine will give we produce energy to turbine, but pumping is something that we need to get into our system. So based on assumptions, we assume that both of the surface is exposed to atmospheric pressure. So we can exclude the P1 and P2 because P1 and P2 is equal. And the next is elevation 1 is 0. We assume this is the reference, our reference, starting our reference. We can take carbon from here, but if we take a minus, so it's going to be a similar. So we start with this level. That elevation point 1 is equal to 0. And the next is the water level, because there is no significant change of the elevation. So we can assume that the velocity in point 1 and point 2 is very low. So we assume the velocity is not inside here, but we take assume we take a reference from point 1 and point 2. So the velocity here absolutely not 0. But we take reference from point 1 in this surface area and this in the other. So we can assume that the velocity equal to 0. And the last is there is no turbine in this system. So we have simple equation that the pumping energy will be equal with the elevations plus friction. So it makes sense. Right? We have a higher friction, so it means we need higher energy into the pump. We have higher elevations, it means we need more energy in our pump. So it makes sense. So at the end, the pumping head is 120 millimeter. Because 100 plus 20. 100 from the elevation and 20 from frictions. And the next is we still need to find what is the energy from the pumping. So just input energy equal to mass flow rate multiplied by gravity and head. Head is we just find head is 120 meters and mass flow rate. We knew that the volume flow rate is 115 meter cubic per second, and just multiply with its density, we can get the mass flow. So the power of pump is 176.58 megawatt. And the next is power for motor, because the efficiency is 85%, because the losses in electricity in the motor and so on. So we input that efficiency is a ratio between pump divided by the motor. So the power of motor is power pump divided by efficiency of, and we have transfer 207.74 megawatt. So it makes sense again that power for motor must be higher than power for the pump, because input must be higher than output, because there is any losses and so. Okay, any question for question one? I think it's a little bit simple compared with question two. Okay, question two, we have here, this is the profile, head profile. Okay, okay. So air at 20 degrees Celsius. So it's essential because we need to define the viscosity, density, and so on coming from temperature properties. Has a boundary layer with sine-wave-shaped velocity profile. So this is, we assume this is the sine wave. So for the sine wave, I think we already familiar that for the sine wave, if you still remember, this is the sine wave. We have 0 and 2 pi. So this is pi, and this is pi. Okay, this is sine. Yes. X is y is something that we already familiar. So in this case, we take this area, nothing from 0 until p per 2, because this is the minimum and this is the maximum. Okay. So take in mind that the sinus profile is minimum 0 and maximum p per 2. So if we input, we already have, if we rotate, yeah, this is x, this is 0, p per 2, we have this profile. Oh, sorry. And if we rotate, it'll be similar like this. Okay. 0, this is p per 2. Gonna be similar. Yeah? It depends how you take a view, x in horizontal or x in vertical. So we back to our hypothesis that we have sine wave. The boundary layer thickness is 6 millimeter. So 6 millimeter is the maximum of the thickness. So it will be equal, P per 2 is in the area of 6 millimeter. And then the peak velocity or the maximum velocity or free stream velocity is 10 meter per second. So this is the value, the maximum value we have when the thickness is 6 millimeter. So this is the profile starting from 0 because mostly condition until 10 meter per second. And we need to calculate the shear stress. I mean, this is at the wall. So the calculation stress tau at wall y equal to 0. So starting here, y at 3 millimeter in the middle and y at 6 millimeter, or at the maximum thickness of boundary layer. And the viscosity of air at 20 degrees Celsius is 1.8 10 to minus 5 Newton second per meter square, or Pascal second. So what we need to define is that 0, 3, and 6. What we have now, because it is sinus, so for the example, this is velocity as a function of x. So velocity is sin x because x we have a function of, for the example, this is the things from x function of y, not y function of x. So it's similar. And maximum 10 meter per second. So if we input y equal to 0, so we have velocity is 0 because y equal to 0. And when y equal to delta 6 millimeter, it's gonna be u maximum because alpha is p per 2 delta. Okay, sorry. And the next what we need to define is input these equations. U equal to sin alpha y, because at y equal to 0, velocity must be 0. And y at delta, so velocity must be velocity maximum, because sin maximum happen on p per 2. So alpha delta must be equal to p per 2. So we have alpha equal to p divided by 2 delta. So this is the alpha value. So every time, so our function is u equal to u max sin alpha is p per 2 delta multiplied by 1. So if you input y equal to 0, you get sin 0 equal to 0. So velocity will be 0. And when y equal to delta, you input in this equation y equal to delta. So you input alpha is p per 2 divided p per 2 delta multiplied by delta. Yeah, and sin p per 2 is 1 because sinus is function of. So this is the representations we have. So now we include in our questions. This is y, and this is u. Oh, sorry. This is y, this is u, and this is u. So u equal to u max sin alpha y, or u max sin alpha is p equal to plus 2 plus y. This delta is y equal to 0. This is y equal to delta. So this is our functions. Where u function of y, not y function of u, but u function of y.
Can you explain why sine alpha y equals 1 at u max?
Sorry?
Can you explain why sine alpha y equals 1 at u max?
Oh, yeah. because here this is the origin. So this is the sinus function. So I think I need to start with here. So this is the sinus function that we already get familiar. That when, for example, this is the random equation y equal to sinus x. We have information that y will be equal to 0 when x is 0, and in one wavelength we have 2 pi. So this is from 0 until or 360 degree. Sometimes you get familiar with radian or degree. So this is the fully function of sinus, and sinus is the function will be from 0 until 1. So this is will be equal to 0 when x is equal to 0. When x equal to p per 2, the sinus, the value will be 1. Okay. So if I multiply y with something else, like y equal to 100 sin x. So this is gonna be 100. Okay. Because sin x when p per 2 equal to 1. Yes.
How do we know it's in radians for this question?
Sorry?
How do we know it's in radians for this question?
Oh, because radian is something more general instead of degree, and that it's common to use the radians instead of degree. Yeah, because I think it's in every like rotational speed and anything we always use radian. Yeah. So if we change with 100, so this is must be changed with 100, and if we change with Umax, so this is must be Umax. This is the maximum that we can have in our equation. So depend on the coefficient we have on the front. And because we know that 0 until p per 2 give the value of the sinus from minimum until maximum, sorry, from 0 until 1, the minimum is minus 1. So we only the constant from 0 until 1. So this is the function. If we have from 0 until p per 2, okay, y function x is this is from minimum to maximum is 1. And if we convert x function of y from 0 until 1, we have from 0 until p per 2. So this is p. And we input into our cases. So our cases is equal like the second one we have in our cases is this one. Our function is 0 at y equal to 0 and maximum at y equal to delta, where delta is 6 millimeter. So this case is equal with this case. Like we have take one portions and then we rotate, and then we have the similarity of function in our case, where y equal to u and x equal to y. It's the vertical distance starting from wall. So our function will be must be equal to the maximum is u max when we have the average one, we have 100 or 1 and so on. So the maximum must be and sinus alpha y, because we define that y not p per 2 but delta. So we need to change when y equal to delta must be similar with p per 2. Because when if we input y equal to delta by delta, so we have p per 2. When y equal to 0, sin 0. So it's gonna be similar. Like we have met analogy, we have case of the sinus functions and we input in straight line. Okay, any questions? Okay.
Why
Yeah.
do we need? Why we don't need to pass another pi to the sine? Because we move the point on the sine wave to the origin.
Oh yeah. So this is just not pure mathematics, but we try to find it as fit as possible. Like if we have a plus like y plus p per 2 and so on, we need to check when y equal to 0 is give you sinus 0. If not, so it's not functions that we need in our case, because when y equal to 0, velocity must be equal to 0. So that's why we have multiplications here. Because in the physics, we have the function that velocity in the wall, if we have no slip condition, must be equal to 0. And if we have plus or minus, it will not give you 0. Or minus or something, but velocity is not a minus in our case. Probably it's also happened in cosinus and so on, but in this case, they asked to make a sinus function because it's already mentioned in this one, sinus wave of the shapes. Sometimes they have always cosinus or have polynomial or exponential function and so on. So it's everything that we need to match in our cases. If we get 0, so we need to make the function match with the physical conditions. And the next is definition of shear stress is, I think it's familiar in tutorial 1 that tau equal to mu u over dy. So this is the viscosity multiplied by gradient of velocity of y. And we input our functions. So tau, because u is u max sin p per 2 delta multiplied by y, take a differential to dy. Using the chain rule, I think everyone is kind of familiar. Which one is, this is constant of y, and this is the constant of y. So the value, this is constant, so we can take out some of functions, cos, infer, because the equation of sinus is top, and this is the constant of the y, so we need to have. So this is the functions of shear stress or tau, and we just need to input in our questions when y equal to 0, 3, and 6. So when y equal to 0, just input from these functions, input to our questions, where tau is 1.8 times minus 5, and so on. U maximum is 10 meter per second. This is U maximum. Cosinus. And delta is 6 millimeters. So 6 divided 10 minus. Okay. When equal to 0, cosinus of 0 is 1. Okay. And cosinus p per 2 must be equal to 0. So the shear stress at y equal to 0 is 0.047. The velocity is 0, but the gradient is not 0. And the next, when in the middle, y equal to 3 millimeters, we have the similar input. So the cosinus must be p per 4 or 45 degree equal to half square root. So we have y equal to, when y equal to 3 millimeter is 0.03. And when y at delta or 6 millimeter, so cosinus of p per 2 is 0. Okay. Because cosinus p per 2 is 0. Because 6 divided by 6 is 1. Cosinus p per 2 is 0. So on the front, multiply 0, we have 0 here.
So the sine wave is basically just it's a transformation.
Yeah, this is the how we make a mathematical function of our physical velocity.
But it basically just transforms the sine wave.
Yes, correct. So sometimes they use exponential function or polynomial function. Everything is okay as far it fit with our physical meanings.
Okay.
In this case, we choose the sinus function that already given in questions. Like let's use something using the exponential functions and other using polynomial. Okay. Question 3. is discussing about a spear attached to a string should hang at an angle of theta when immersed in a stream of velocity of u. So if we have spear, there is a line or string, and then its velocity u. So it must be inclined in degree of theta. So when the velocity of 0, the theta must be 90 degrees. Okay? But at some point when u is not very fast enough, so we make theta between 0 until 90 degrees. Okay. Because when u0 is only hydrostatic functions. We have another version for theta as function of sphere density. We have density of sphere, rho s, and diameter and drag coefficient, Cg, and the fluid velocity and density. The meaning of density here is density of fluid. Not density. We have two density of sphere. So this is the solid and this is density of fluid without other notations. And then we need to calculate where of the theta when we define the density of sphere and so on is this one. First, we need to define theta, function of all of these equations, and then define the drag force, and then define the what we don't know is the weight of spring itself. Okay, so this is the free body diagram. So I think you already have familiar that if we have a lot of force applied in our cases, we can apply free body diagram. First, we have this drag force, weight coming from the sphere, and there is tension of string that makes the system balance because this is not running anywhere, so it must be in balance conditions. First, the system is in equilibrium, so the force in x and y are balanced, and moment and so on. So that I think equation of force is sufficient enough to define in our equations. So in x direction, in the positive, so this is x positive must be equal to x negative, and y positive also y negative. So in x directions, this is fg must be equal to t cos theta because it is okay. And then in y directions, the positive of y must be equal to with negative 1. So this in theta must be equal with w. So this is t multiplied by sin theta, so it must be in this direction. And for x, it must be in this direction. So we have this is t in x direction and this is t in y direction. So we have two equilibrium in x and y directions. And then to simplify, we can divide the sin because we have two functions and we want to simplify in one equation. If we divide this sin theta equal to y divided by t cos theta equal to fd, so it will produce that tan theta must be equal with weight divided of drag force. And then we need to define what is weight. Weight is the mass multiplied by gravity. Mass of sphere equal to density multiplied by volume, and gravity is just right. And the volume is P per 4, 4 per 3 PR cubic. So the weight of sphere equal with this also. Please to remember that we need to use the density of sphere, not the density of fluid, because this is the weight of sphere. And then the next is we already know W, the weight, and the next is we need to define what is the drag force. Drag force is function of CD multiplied by inertia force. This is the inertia or the mass flow rate multiplied by velocity, the linear momentum of fluid. And because it is, 0.2, and velocity also has the function and so on. And A is the cross-sectional area. So if we have sphere, the cross-sectional area must be circular. We have sphere, and the cross-sectional area of to the flow must be equal with area of circle. So PR squared. So FT is CT of so on. And we input in our questions because we already defined W and FT. They will tan functions. So we have tan theta will be W divided by FT. So this is the weight, and this is the drag force. So we have tan theta will equal with this function. So we already defined theta as function of density of sphere, density of fluid, velocity, diameter, and coefficient of drag. So theta function of 1, 2, 3, 4, 5 variable. And then the next is we need to calculate theta if we define the density of sphere, diameter, CG, U, and rho with this value. So just input anything in our equations that tan theta equal to blah, 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 blah. We input this value. This is the density of sphere of 5,500, cavity, diameter of sphere, and this is CG. This is density of air, and this is the velocity. So we have theta equal to 5.65, and take inverse using your calculator. We have theta equal to 79.96 degrees. Or you can take radian in our case, depend on your preference. Okay, any questions? Okay, next is question 4. It's a long question, but I think it's quite simple for us compared with question 2 or question 3. We have hydraulic jump. So this is the hydraulic jump. So I think it's more appropriate in civil engineering, but well to know for our understanding. This is like in designing dam and so on, when you release water in high velocity and then suddenly have discharge with atmospheric, so they can expand, like making hydraulic jump, like expanding the velocity. Because this is there is a down and this is high velocity and then they will expand. So flow in a 150 millimeter wide channel jump from a depth of 50 millimeter. So this is the wide W is perpendicular to our screen. So this is the wide 150 millimeters. This is the wide, this 150 millimeters, and this is the height. Is 50 millimeter at point 1 and expand to 150 millimeter at point 2. From 50 to 150. And we need to write an expression for continuity or the conservation of mass using the velocity and depth. And then the next is consider the momentum principle. We need to show the velocity using these equations. So we need to force ourselves how to match these equations. And the third is the upstream and downstream velocity. if we have these channels, and then third number, 0.1 and third 0.2. Third number is the ratio between inertia and gravitational force, and volumetric flow rates, and then the last is the energy losses is the function of this function. So we need to estimate the rate of energy losses. Okay. For the equation 1, we need to divide the expression for continuity using the free function. So basically we have mass flow rate and in must be equal to, because this is steady condition, and rho VA to rho VA. Okay, because this is incompressible flow, so rho 1 must be equal to rho 2. So we can sorry, 1A1 must be equal to 2, because A is W by H, as we have no H and W perpendicular to our screen. We have V1 W H1 to V2 W H, and taking out the W, we have V1 H1 equal to V2 H. So at the end, from the mass flow rate equations, we can get these correlations. And the next is consider the momentum principles. Show the velocity are given by the 1 square is equal to half g ratio of its and proportion of its. First, we divide the momentum principles. So this is the streamline. So we have the two force here because of hydrostatic pressures and because the change of linear momentum in our mass flow rate. So force equal to linear momentum mass flow rate multiplied by velocity, or mass multiplied by accelerations. And then for the force on the left, equals direction, positive, and this is in negative x directions. So this is force equal to pressure multiplied by area, and the average is must be the center of hydrostatic, and this is also equal more the force because hydrostatic pressure applies. And this is the linear momentum. This is inlet is negative and outlet is positive. So this is both in x directions. Okay. P1 is positive x direction, P2 is in the positive x direction. But for the mass flow rate, this is inlet is negative to the cross-sectional area, and outlet is positive to cross-sectional. So we have positive for outlet and negative for our using the Reynolds transport for linear momentum equations. So this is the for sigma f. So this is sigma f, and this is mass flow rate multiplied by velocity, or linear momentum of our fluid. So we need to define force coming from pressure, and it must be equal with mass linear momentum in our fluid. The change of linear momentum. So if we input in the preface one, so sorry, preface one, we have these equations. If we input here, we taking out the y or the w, so we must be have equal rho v squared x minus in outlet minus inlet must be equal with the change of pressure in positive X and in, minus in negative X. Because the average is must be half of H1. So the average, I think is the same in your coursework here. We have in the practice. The average must be seperti ini. So pressure rho GH, pressure H is the H represented equal to half H1. So we have half rho GH1 square. And we input in our questions and you can calculate the reading, the functions. And using the continuity in practice one from the mass volume inlet must be equal with mass volume outlet. So V1 H multiplied H1 must be equal with V2 multiplied by H2. So V2 must be equal with V1 H1 divided by, so we change V2 with constant and we get this. At the end, with the same mathematical concept, you can manipulate your equations to fit with our destinations. Actually, it's coming from here. I think it's already defined the V1, but again, the function need to define must be equal in this form. So you need to do some mathematical magic or mathematical things to make our equation fit with the questions. And then the same, similar from this equation, if we apply V1 equal to V2 H2 divided by H1, we will have these equations. So starting with these equations, you are not inputting V2 as the function of V1, but you input V1 as the function of V2, will give this equation. So I think it depends on how you change the questions. And C is determine the upstream and downstream velocity, because upstream and downstream velocity is function of G and elevation. So input H1 equal to 50 millimeter and H2 equal to 150 millimeter. To our equations, we get V1 is 1.72 and V2 0.57. So it makes sense, right? We have high velocity and low velocity. Because there is expanding of intersectional area. And third number is linear moment inertia divided by the gravitational force. So this is the and shape of third number. Input V1 and H1 in third number 1 and the third number 2. So this is you get a high third number, and this is subcritical because third number less than 1.
What is a third number?
Or third number here. So I will so this is in your, I don't know, is it already explained by Ben or not, but it will give you the third number is ratio between inertial force to gravitational force to define is it subcritical, critical, or supercritical. So, oh yeah, okay, yeah, this is the inertial force to gravitational force. It will be available on your blackboard, yeah, to define the third number. So it's analogy with the Mach number. So in fluid mechanics 2, you have Mach number. In supersonic or subsonic sound wave But for number 4, the open channel flow. And last, we need to define the volumetric flow rate. So we know the volumetric flow rate you can calculate in point 1 or point 2 must be similar because mass flow must be similar. So the volume flow rate must be similar. We have volume flow rate 0.01 to 86, and the energy loss across the chart. So this is just input from our equations. This is for the head losses. Sorry. Meter cubic in meters, and we multiply with rho GQ Derive to get the energy losses because the losses is vinegar. So loss of the energy in our systems. Yeah.
Where did you get E equal rho GQ delta H from?
Oh, this one.
Yes.
This is the same in question 1. Mass flow rate multiplied by H. M dot GH. Because M dot is rho. Because we don't calculate the mass flow here, so we convert in rho. But it's similar with question 1 when we calculate the energy for pumping. So energy loss is similar with pumping, here similar with turbine and so on. In the unit, I mean. But they have a different definition. It's coming out from system or it coming in through our system. Okay, that's all for our tutorial today. Do you have any questions? I think this for the open channel, I think it's not covered yet by Ben, but maybe in the next lecture, he will discuss more about the open channel. As you all take the lab experiment, okay, because today is the last session for making up the lab session. So if you missed the last experiment lab for VR, wind smoke tunnel and Bernoulli, just come to A4 until 30 past 11 or half past 11.